Intermolecular forces. This is also, again, an important topic. Uh, if you take a biochemistry class, you're going to spend probably the first maybe few lectures talking about these, because what stabilizes the structure of proteins or DNA or even lipids and carbohydrates, especially the first, few, are intermolecular forces. So those structures, they have strong covalent bonds between them or ionic bonds, but then they also have to have some stabilization force to make that protein structure more stable. So there is where you have your intermolecular forces. Otherwise, it falls apart. Again, all the parts of it. So intermolecular forces, just a quick review. It's the word inter means between two molecules. So if you have molecule 1, I'm going to call it M1. And if you have molecule 2, this thing right here between them, which we usually show, and let me actually show that right away, this force between them is called an intermolecular force, or IMF. So be careful. Intra is usually within that. So intra is within, intermolecular. For example, if I have, a covalent bond, that's an intermolecular, that's within. Chemical characteristics, chemical properties, that's where they rise because of those, the bonding here. Again, intermolecular forces are on the outside. So you can have two methane molecules, for example, interacting with each other versus within that. Very important distinction. I cannot tell you how many times we say this and there's usually a confusion. Sometimes the terminology can be confusing. So there could be some kind of an interaction between these two. Okay, let's look at the three types. You have dipole-dipole. So from the difference of electronegativity from basic Gen Chem really, C has an electronegativity of 3 and H is 2.1. So when they're aligned this way, the chlorine, or the chloride in this case, is a delta minus. So it's attracted to the hydrogen, which is a delta plus. That's what causes the attraction. Plus to minus. So again, it's usually plus to minus like that. So they're oriented or aligned in a way that makes that interaction possible. Here's another example from organic chemistry is acetone. So on carbon, it's delta plus. On oxygen, it's delta minus. Once again, look up the electronegativities. And they're aligned in a way where, again, the positive end of carbon on this molecule, middle molecule, is close, or it's aligned in a way that enables it to interact with the negative, the delta negative on oxygen, and on and on and on. So that's what dipole-dipole. The word dipole-dipole means two poles, two poles. That's what di means. And if you think about it, you have two poles here. You have the delta plus and you have the delta minus. So that's the two poles right here. And then the delta plus and the delta minus. So how do we look for these? Well, look for polar compounds. For polar compounds. We're going to discuss them more in depth. The second one, probably the most important one in biology, in biochem is hydrogen bonding. You're familiar with this. This is really nothing but a review from Gen Chem. Well, this one is really a special type of dipole-dipole, except what you have here is you have H, in this case, let me use a different color. H is attached to N, O, or F. These three atoms are the most electronegative atoms. So the bonding, the intermolecular force is very, very strong, is very, very strong. So delta plus is on H. Let me use a different color for them. And the delta minus of the other molecule is on O. So you see the interaction between them. Now, the word bond is a really confusing, because you might think that this is like the covalent bond, but it's not. It's just the name that has been just adopted, and now it's kind of part of the tradition of chemistry, but it's still an intermolecular force. So you can think of it as a hydrogen intermolecular force. Don't let the word bond make you think that this is like a covalent bond. So it's between two atoms in different molecules. So hydrogen bond. This is very, very strong. This is the strongest from the ones we're going to examine. So look for hydrogen, nitrogen, hydrogen, oxygen, hydrogen, fluorine bonds. And again, you always draw your intermolecular force between the delta negative on the electronegative atom and an H in the other molecule. You know how important this is. If it weren't for hydrogen bonding, DNA would not be possible. Again, this is what's holding the two, the double helix, right? Remember, if you remember that, that's what holds it together. And finally, you have the London dispersion forces or van der Waals. They're actually a little bit different than van der Waals, but we're going to use that terminology just to go with your book. These exist in all molecules, okay? So they apply to all molecules. Polar and non-polar, but they are more effective in non-polar bonds and non-polar compounds. So once again, look for those carbon-carbon, carbon-hydrogen bonds. But they still exist in everywhere. Very well. What makes it possible? Well, I'll give you a simple review from Gen Chem. Well, if you have an atom, let's just look at a simple atom. If we have an atom and we have the nucleus here in the middle, I'm going to use it as a square so you can see the distinction here. And you have an E, let's say the electron is now on this side right here. And then you have another atom. And the electron is also on the left side. Notice that at a given moment, the electron here, this one, can have an opportunity to interact with the nucleus in the other atom simply because this one is on the other side. Of course, when it comes back, it's going to cease, it's going to stop. And it happens on the other way around. Imagine if you have so many atoms that at a given moment, by probability, you can have these interactions, and they become what we call, they're momentary changes or temporary dipoles. So these are called temporary dipoles. They're not permanent like the other ones. They turn on and off, turn on and off. Imagine, they do that in some of those buildings where they, like in, let's say a big building where they turn off the rooms at a given, at a given rate, and then they create some kind of I don't know, a lighting pattern or something like that, like in downtown Chicago, etc. Just to give you an idea. That's the idea. Quickly, there are two important factors that affect van der Waals. Number one is the surface area. The larger the attractive force between two molecules, the stronger the intermolecular forces. Makes sense. If you have a larger surface area, you can have more of these temporary dipoles. Look at the negative, delta negative, and the delta positive. Versus if you have a smaller surface area, you have less interactions. So again, basically, in a sense here, longer and bigger molecules. That's what you want to look for. These are smaller and what we call, they have branched. So we'll get to it in a second in the next video. The next one is something called polarizability. Polarizability is the measure of how the electron, cloud, and atom responds to changes in its electric environment. So polarizability is basically, again, you're looking at the electron cloud. That's where on the outside. If you have a larger cloud, once again, you can have an increased surface area. So iodine is a bigger atom because if we look here, here's F, here's B, here's Cl, here's Br, and here's I. And we know down a group, the size increases. Once again, see how we're revisiting this. So the bigger the size of the atom, the more polarizability it has, which increases, again, the surface area. Again, that is what's happening here. An analogy of this is that I always like to think about is that imagine the F atoms as a golf ball, right? So if you have a golf ball right here, if you try to squeeze on the golf ball, you're not going to go anywhere. I mean, it's not going to move. Imagine that those electrons are so close, right? In comparison to the iodine, to the nucleus, making it, again, a more compact ball, right? So that's the idea here is they're so close and the electrons are not polarizable, or they can't, this electron cloud cannot move or be distorted. Imagine now that this right here, the iodine is a pillow. So we have I. Well, if you squeeze on a pillow, again, it can move up and down to the sideways, whatever ways you think about, right? So, so again, that would make it very polarizable. Less polarizable. So that's the idea here is, again, the distorting of this electron cloud.